You should be okay now. Just don't try again.
Cool. Okay, yeah, thank you. Go ahead.
Okay, cool. Well, thank you for the introduction, and thank you for the organising committee for the invitation to speak today. It's great to be here. Good morning, afternoon, evening to everyone. My name is Hayden Robertson, and I am a PhD candidate at the University of Newcastle, Australia. And today I'm going to give you a quick rundown on some software that myself, Andrew Nelson from ANSTO, and Isaac Gresham from the University of Sydney have written, called Refellips, and it's for the analysis of ellipsometry data in Python. So a quick overview of the talk today. We'll start off with talking about what ellipsometry actually is, what you can measure with it and why you might want to use it. And then we'll dive into why we decided to make Refellips and what Refellips actually is, before going into a brief demonstration on how Refellips works, and hopefully that's not too boring. And then we'll dive into an application, which I think is one of the coolest features of Refellips, being able to co-refine multiple different data sets from different techniques. So, for hundreds of years now, light has been used to investigate lots of different physical properties of various materials, like refractive index, dielectric constants, and say thicknesses. So today though, ellipsometry is more of a ubiquitous technique, especially in the field of surface science, where we have resolution right down to the sub-nanometer level, but also up to the micron scale. So typically with ellipsometry, you'd be looking at measuring things like thin films. So for example, you might have an air solid setup for oxide layers, or you might be looking at a solid liquid setup and you've got absorbed polymers in a fluid cell, for example. Or you even might be looking at an air liquid or a liquid setup, potentially even using a Langmuir trough to have a look at absorbed surfactants at interface as well. And from these particular measurements, we can get a really good idea of layer thickness and roughness, and if it's applicable, a volume fraction of solvent within that particular layer as well. So we can also measure things like semiconductors and photovoltaic ellipsometry, and that can tell us information about band gaps and also a wavelength of maximum absorbance for those photovoltaics. We can also use ellipsometry for Brewster angle microscopy to visualize, say, monolayer formation, so really probe those interfacial kinetics. So that was a brief overview of what we can measure with ellipsometry, but what about how it actually works? So the principle of ellipsometry lies in the change in polarization of light upon reflectance from a stratified interface. So if you irradiate your sample with a light source of known wavelength, known angle of incidence, and a known polarization state, when the light reflects off your sample, you can measure the change in polarization from that incidence state. And this will give you the two reflectance coefficients, RP and RS. And from these reflectance coefficients, we can then calculate the two ellipsometry parameters, delta and psi, and you can see those up the top here. And delta is simply the complex angle, which tells us about our phase information, and psi is the angle subtended from RP and RS in the schematic you can see. And because we're using lamps or lasers with relatively low power, it's a non-destructive technique, but it's also a great technique because it's relatively fast and simple, and it's a good complementary technique to a reflectometry experiment. And typically I would use an ellipsometer to pre-characterize my samples prior to popping them in the beamline, just to know if they're suitable or not. So a little bit of insight into the particular research that I'm interested in are polymer brushes. So these thin films just consist of polymer chains which are densely grafted to a silicon substrate in this example, so that the chains are forced to interact with each other and extend up normal from the substrate. And the particular types of polymer brushes I'm interested in are thermoresponsive. So there's different types of stimulus responsive brushes, but the thin films I'm interested in are thermoresponsive, meaning that they change their conformation in solution depending on the ambient temperature. So in short, I guess when the solution is cold, these brushes or thin films are quite swollen and they're quite thick. Then we increase temperature, the film shrinks and it decreases in thickness. And we have extensively done neutron reflectometry on these particular films, characterizing their behavior as a function of lots of different stimuli rather, whether that be temperature, solvent composition, or electrolyte as well. And neutron reflectometry is really only one of the techniques that can tell us about the subtle changes of the internal structure that are happening inside the brush with such a high resolution. But of course, because neutron beam time is very, very precious and for the most part is not readily accessible, we have to really carefully pick our conditions that we want to do with reflectometry. And this is where ellipsometry comes in. So ellipsometry is actually perfect for this because it gives us a rough overview of the brush behavior and it can tell us about our average film thickness for a particular condition that we're interested in, be that a different temperature or a different solvent composition or different ionic strength, for example, and see how the brush responds in these particular conditions. But it's important to note that ellipsometry only tells us really the average thickness, or you can see here in this figure, the swelling ratio, which is just the hydrated brush thickness divided by the dry brush thickness. And it doesn't tell us anything about the internal structure of these films like neutron reflectometry does. So in doing all these types of preliminary experiments with an ellipsometer, we quickly acquire a lot of ellipsometry data, which when you're using some sort of proprietary software that doesn't allow the batch processing of data, this can be quite time consuming. And I guess herein lies the reason that Refellips was born. So back in the early days of my PhD, I was collecting a lot of ellipsometry data. And I had this great setup with automated temperature controllers and pumps and everything. And it was great at collecting the data. But when I went to actually do the analysis, the software that I had access to at the time wasn't so great. It was proprietary software that didn't facilitate any sort of batch processing whatsoever. And I remember dreading the analysis at the time because just mindlessly clicking away in the GUI, taking probably 10 minutes per data point. And when you've got hundreds of these data points, it adds up really quickly. And it just at the end of the day, GUIs aren't very conducive to batch processing. And I remember thinking that there had to be a better way. So I did some digging and I realized the actual calculations for delta and psi, those ellipsometry parameters, weren't so difficult at all. And this is kind of the birth of Refellips. And Refellips is capable of readily or rapidly batch processing ellipsometry data, making my life so much easier. So one of the main things that I use ellipsometry for and Refellips is actually the spatial mapping of surfaces. So with ellipsometry, if you're lucky enough and you have an automatic stage as well, it's quite easy to collect data from multiple points across your surface, or 500, for example. And analyzing this data in another ellipsometry software package would take days, loading in each individual data file, making the model, fitting the data, then copying the results out to an Excel spreadsheet. It just takes so much time. But with Refellips, it's super easy. We can just point the software to look at a particular directory and essentially just press go. And minutes later, we've got this wonderful spatial heat map waiting for us. And this type of pre-characterization is super important for any sort of reflectometry experiment, because as I mentioned before, we all know that beam time is very, very precious and we don't want to waste any of it. So it's really important that we know if our sample is suitable or not for a neutron or X-ray reflectometry experiment before putting them in the beam. So I think it's safe to say that I definitely wouldn't have the extensive ellipsometry data set that I have today without Refellips. I'd still be sitting behind the computer, clicking, loading in that next data file and clicking fit. One of the other key concepts that we had in mind when designing or building Refellips was reproducible data analysis. And I'm sure this is nothing new to everyone in the audience here. but reproducible research and open science, all the above, are really becoming a critical pillar of data analysis and data science. And Refellips facilitates being reproducible and open science by being open source itself and completely transparent in everything that we do. So users have the option, if they like, to look under the hood, look at all the calcs and see how everything is implemented, and even implement some custom code if they wish. And we welcome any contributions to the GitHub project as well. So Refellips is designed to be used in a notebook environment or just a simple Python script that you can either execute locally or add to an existing pipeline. And if you're using it in a Jupyter notebook, say, these notebooks are really powerful because they contain the original data, the original code, and the original output. So this makes it super easy to pick up the notebook and hand it to someone who's potentially new to the field, like a new student, which you can do because Refellips is free and not tied to any particular hardware. You could hand it to them and you could say, reproduce this analysis just for practice and learning purposes, or you might be wanting them to actually confirm something you've done. And this is something that can be quite tricky in a GUI. Clicking in the right places all the time, loading in the exact same environment. As I've mentioned before, GUIs just aren't conducive to reproducible research as a notebook might be, for example. And one of the last real features of Refellips that I'll share broadly is model sharing. And I think that Refellips's greatest strength is that it actually leverages the architecture of Refinex. And I'm sure most of you have heard of Refinex before, the neutron and X-ray reflectometry analysis package written by Andrew Nelson. And because these two packages, Refellips and Refinex, share the same architecture, it's incredibly easy to share models between the two. So if you're familiar with Refinex, you will find Refellips really, really easy to pick up. And if you have existing models for your neutron or X-ray samples, you can very easily pick those up and apply them to an ellipsometry data set just by updating those SLDs to refractive indices and extinction coefficients, for example. And something really cool that comes out of this model sharing ability between Refinex and Refellips is the ability to co-refine data sets. So this is something more that I'll touch on a little bit later. So at this stage, I've mentioned a couple of key features that I think Refellips has that are great and we've thought of when designing the software. In particular, being able to batch process data and being completely conducive to reproducible research. Just to touch on again, it's open source, meaning that it's free, it's unlimited installs, and also meaning that it's fully cross-platform compatible because it's in Python, I guess. And whether you are going from a Mac operating system or to Linux or to Windows XP to Windows 11, you'll be able to use Refellips. Most importantly as well is that it's not ellipsometer dependent, it's ellipsometer independent. So it's not tied to any particular hardware and it will work with any ellipsometer that you can export the data into a normal text file. And there's also extensive documentation on all the calculations we do, how the software is set up, all right down to what effective medium approximation might best suit your sample, for example. So at this point, we've heard a little bit about what Refellips is and why we decided to make it. So now I'm going to dive into a quick crash course on what Refellips is. And for this, I'm just going to use a simple oxidized silicon wafer, little schematic down here, but I'm sure we all know what that is. And for this demo, I've also only chosen a data set that relates to one point on the surface, a single wavelength, and 8 angles of incidence. And you can see here on the right, the flowchart describing the model and fitting process that happens in Refellips. Hopefully this isn't too foreign, it's not too uncommon, but I will highlight the relevant sections as we pass through them. So to start off with, we'll just load in our data essentially. So for this particular example, we're just using a nice generic data format. It's essentially just 4 columns of data. We have a column for angle of incidence and wavelength, and we've got columns for psi and delta, those 2 ellipsometric parameters that come out of the measurement. And Refellips has functions to load in generic data sets like this one, but it also has functions to load in the direct output files from various ellipsometers as well. So you don't have to manipulate your data before you use Refellips. And if we don't have your ellipsometer already as a custom function loader, we're happy to make one for you, or alternatively, we welcome you to contribute to the project as well. And most importantly as well, if you are doing a multi-angle, multi-wavelength measurement, so a variable angle spectroscopic ellipsometer measurement, this will become a 2D data structure, and Refellips is quite capable of handling such data. So the next step, once we've loaded in our data, is we have to start creating the model which best represents our system. And we start by creating components for each layer within the system. And for this particular example, because we've just got that oxidized silicon wafer, we're just going to have the optically infinite backing of silicon, and then a finite silica interface, and then an ambient phase of air on top. And these components contain all the physical properties of these materials. So they have information on the refractive index and extinction coefficients, the thickness and roughness and properties like that. And you can see here there's a couple of different ways to load in these properties. Refellips comes preloaded and distributed with some common materials, so silicon being one of them, and we can use the load material function for that. Alternatively, you could define a Cauchy model for your particular material, and you can do that using the equation down below. Or alternatively as well, you could just load in a dispersion curve, which is just columns of columns of wavelength and refractive index and extinction coefficient. And this refractive index.info library has an enormous database of many different dispersion curves for many materials. So once we've loaded in and created the components, we'll now define some more parameters for those silica layer. We'll start off with saying it has a rough thickness of about 30, and we'll let it vary between 1 and 35. And then once we've made those components, we assemble them into the structure from fronting to backing. So air is the component that is irradiated first, and then right down to silicon, which is the component irradiated last. And then we load in the structure into what's called the model, and the model is then used to calculate theoretical delta and psi values. So once we have our theoretical model and our experimental data set loaded into Refellips, we can quite easily create the objective. And the objective is what determines the residuals between our experimental data and that theoretical model. And you can see here that the scatter plot, so the dots are the experimental data set and the solid curves are the theoretical values. For psi, the red data set here, the experiment and theory kind of overlap already, and this is indicative that our dispersion curves and our refractive indices are pretty much spot on. But the delta values here are a little bit off, which means some of our thicknesses are a bit off because we've got some of that phase delay in there. So we've now created an objective. Let's actually go and fit the data. I've fit the data here using differential evolution, very overpowered for this particular case, but of course you could use something like least squares. You can actually use anything that the RefNex package offers, which is also what the SciPy curve fitter offers. And then we can see here that we ended up getting a silica thickness of about 20 angstroms. Data and theory look great, they overlay. And we also have a refractive index profile. Now I'm sure to you, everyone here, this doesn't look too bizarre, but in ellipsometry, it's not too common to actually see a depth profile for a refractive index. But this is just analogous to an SLD profile. And I guess the key takeaway is here we've got the mechanics to make these refractive index profiles. So all in all, in doing all of that, we only ended up needing this amount of code. So it was only about 20 lines of code. And the scripts are incredibly straightforward to set up. You can use any of the templates in the docs that we have to help you get started. Readily modifiable to any sort of analysis, but you can also change them to do a very complicated set of analyses as well. So they're all there to help you. And of course, if you need assistance getting started or anything like that, feel free to contact us. Or, yes. And then the last thing, I guess now I'd like to touch on is the model sharing ability of Refellips in a little bit more detail. So we're finally here. I've kind of teased this co-refinement all the way through, which I think is one of the coolest features behind Refellips, the ability to co-refine an ellipsometry data set with a neutron and X-ray reflectometry data set. And this is something that has not been demonstrated before. So the way we go about this is very, very similar to optimizing a single objective. So we still create that theoretical model and load in the data for each of the objectives. But once we've actually done that, we then load each of these objectives into a global objective. And it's important to note here that for the reflectivity data sets, we will not be weighting the data from any sort of error. We're going to we're going to fit the data as log R versus Q. So we take away that weighting from this particular aspect. And we are going to weight the data using multipliers. And this is our kind of naive attempt to make sure that the data or each of the data sets equally contribute to the overall fit, to the overall chi-squared values. And I guess this is something that we're still trying to figure out, and everyone's still trying to figure out whether it just be neutron or X-rays, because we're illuminating different areas, we're different sample volumes, and of course we're probing different physical characteristics. But the mechanics to do this type of analysis are all here. So why might you want to co-refine your data? Well, I guess the thing that comes to mind first is it would improve your model confidence, and you can be more confident that the final parameters that you get out from your fit best represent your physical system. And of course, some techniques are more sensitive to some parameters, or you might want to minimize destructive radiation to your sample as well. And alternatively, even if it turns out you can't co-refine your data sets all at once, we can still use the ellipsometry data to feed into a reflectometry analysis data set. So something like feeding into a prior or even feeding into a multiple area model if you have to go down that path, say. So if you're lucky enough to have a sample that you have got ellipsometry data for, neutron reflectometry data for, and X-ray reflectometry data for, your final data set, the co-refined data set, might look something like this. So this first figure here is the ellipsometry data set for a polymer brush, one point across the surface, but this time we've got 8 different angles of incidence and 12 different wavelengths. And then in the figure B here in the middle, we have our X-ray and neutron reflectometry data, just offset for ease of viewing there. And then our final figure here is our depth profile. And we've got on the left y-axis SLD, and on the right y-axis we've got refractive index. And you can see here that each of these different depth profiles is analogous in their structure. And this is being able to do this co-refinement across multiple techniques is something that hasn't been done before, and is something that I think is really cool. Okay, so thank you everyone for listening. I hope that I've inspired you to think of different ways that you might be able to use Refellips, whether that's its batch processing ability, or it's being conducive to reproducible research, or even using it to inform your reflectometry experiments. I hope that you find a use for it. But as I mentioned before, we welcome all contributions and feedback to the project. There's a QR code to the GitHub page here, and bookmark this because we've got a paper on the way, so stay tuned. And I'd just like to say an enormous thank you to Isaac Gresham from the University of Sydney and Andrew Nelson from ANSTO, without which Refellips definitely wouldn't be where it is today. Thank you.